Hopefully you can all see this. My apologies for not
Now we
being there
can.
in person.
Perfect.
Okay, perfect. So hi everyone, my name is Gabor Samu. I'm a senior product manager with IBM software. I'm part of the team that part of the product management team for the LSF product family and its sister product Symphony. So going to be presenting just very briefly just a look at orchestrating hybrid quantum classical workflows with LSF. I do want to acknowledge the contributions of my colleague Vadim Eliseev from IBM Research. He's a research scientist there, and because his group was instrumental in putting together the integration scripts that we'll be talking about. So I guess in the interest of time, I mean, point here is that, plus ça change, as we say in French, HPC environments are heterogeneous in nature. We're now talking about adding QPUs to these environments. These are devices that have specific characteristics that need to be considered and managed by both the resource management layer and the workload management layer. How do we get here? So, not going to really give an overview of QRMI because I think everybody here, is well familiar with that. But our team in IBM Research had put together some integration scripts using the LSF hooks, which I'll talk about a bit more, to enable the execution of tasks on IBM quantum processors. The plugins themselves have been made available on on an open source GitHub, so they're open source components. Provided the links here so folks can look at these and see what we've done. So not only are these at the really execution level for the jobs, we also created a plugin to collect resource information from quantum processing units. And that's something that can be fed into the LSF scheduler and used to make scheduling decisions as well. So onto the workloads. I know Vanessa had spoken about this as well. So with the work that the team completed in research, we were looking around for a candidate job that we could run through LSF. We found this in the form of the sample-based quantum diagonalization, or SQD example, which is part of the Qiskit add-ons. Those used to estimate the ground state energy of a molecule, which is something fundamental in chemistry and material sciences. And what's important here is that this algorithm has been demonstrated at a large scale, running at RIKEN on a Fugaku supercomputer on IBM QPUs. So that this was really a good example that we could run through the LSF scheduler. And mapping this to LSF, we took the monolithic SQD script, which is provided in the Qiskit add-ons, and we actually decomposed it into 4 separate programs. And I'll say a bit more about that, but just in brief, the first step is mapping classical inputs to a quantum problem. Second step is the optimization of the problem for the specific target quantum processing unit. Then the third step, of course, is executing on the QPU, and then the fourth step is collecting the output, the stream from the quantum processor, and performing post-processing on that information. Step 2 here uses the local unitary cluster JASTRO quantum circuit ansatz, which is constructed with knowledge of the target quantum hardware topology. So that's something to mention as well. Just want to mention, for this, one of the motivations for breaking this down is that we observed that these different steps of the workflow, some of them were CPU bound, so step 1 and step 4. Step 3 was not very much CPU bound because that was, basically a placeholder job that was handing off things to the quantum processing unit. So that was just kind of holding a spot or a job slot on a classical system, and that doesn't really have any intense resource requirements. So that's just a bit about the workflow, and this was submitted using so-called dependencies, job dependencies. So these 4 distinct stages were implemented as scripts, And these scripts, would exchange information via parallel file system. So you have like a loose coupling between the stages. And each stage is submitted to the workload manager as a job, job I. So where I is equal to 1 from 1 to 4. And the submission chain enforces a dependency rule that job I plus 1 can only begin when job I completes successfully, and so on. So that's just a bit about the workflow that we selected. So we took this example and we actually made some effort to decompose it, so that we could kind of run it across the workload scheduler to gain some efficiencies there. So this is a bit about the overall architecture. So this is about the plugins that we created for LSF. So this essentially represents the execution lifecycle of a quantum job submitted to LSF with the user provided, explicit topological specifications for QPUs available on the IBM Quantum platform. So I guess going from left to right here, the user submits a job via the LSF bsub command, and they specify quantum topological requirements alongside some classical resource requirements. They provide the name of a QRMI template environment, which contains the IBM Quantum platform access credentials, and a newly developed extension of the bsub command known as the esub.qpu that parses the quantum specific input and arguments. It parses the quantum specific input, and then it augments the job metadata, I should say, accordingly. So the LSF esub itself is a generic hook into LSF, which you can use to intercept job submissions before they enter LSF. So that allows you to do validation or modifying or enriching or rejecting jobs based on site-specific policies. So we took advantage of this for this purpose. So this augmented job description is received and processed by the standard LSF daemons, and the job is dispatched to a selected compute node. So before the main workload begins, there's a new component called jobstarter.qpu, which is launched, and this job starter script executes immediately before a job starts on the execution host. And that enables you to do some custom runtime setup or environment preparation as well, which is specific, for a particular use case. And in this case, we're using this of course, to set up the environment for the quantum system. So from there, we're querying the IBM Quantum platform using the Qiskit REST APIs to receive kind of a list of available quantum devices for the particular user accounts, along with their topological and operational characteristics. And then we would select a device whose topology and attributes satisfy the user specified requirements. So in this case, it's the number of qubits that the user was asking for. Then this would generate the device-specific QRMI environment variables and export them to the subsequent workload. And then next, the actual workload is executed on the selected QPU with QRMI orchestrating this full lifecycle of the quantum job. So the jobstarter.qpu actually selects the best possible QPU, according to an algorithm that we built into it. And this includes, the QPU attributes, which we organize into a matrix. The quantum resource requirements are extracted from job metadata, and then we assign priorities based on this order during submission. So it does some kind of sorting here. So there is some rudimentary intelligence that we've built into this to help kind of choose the most suitable QPU, and it also considers the queue length, so that basically the number of jobs that are queued up on the QPUs that you have access to. So that's kind of just a very quick look at what this looks like in terms of using all of these standard LSF hooks to be able to run this workflow, essentially, which is comprised of 4 LSF jobs. So I'd mentioned, some of this earlier. So, this kind of repeating some things here, but this is kind of a baseline that was established showing the wall clock time of each stage in the SQD workflow. And this was from a testbed environment that the IBM research folks had set up. And again, we see, as I mentioned before, stages 1 and 4 are very much CPU bound. Stage 3, which only runs on the QPU, only takes about 30 seconds of the QPU, but it could end up pending for quite some time, depending upon how busy the quantum processors are in the IBM cloud. So it basically blocks a job slot until the QPU is free. This provided some of the motivation to kind of break down the monolithic SQD Jupyter Notebook into 4 scripts, which could be treated by the workload scheduler as 4 separate jobs. And then this would allow us to do some, overlapping potentially of tasks, right, for efficiency purposes. Yeah, so really this is about trying to get better use out of the environment overall. Oops. I realized I didn't flip the slide. Okay, sorry, this is what I was just speaking to a moment ago. In terms of observations that we've made and some feedback that we've received, certainly from the commercial HPC or enterprise perspective, accounting is very important, and I think it came up in some of the other discussions. So, questions like, what resource or QPU was consumed, how much did that cost? Was it used well, etc.? So I think that these are important things. And to echo some comments earlier, I think there's some consideration about where this would live. Is this the responsibility of the resource management interface or the workload scheduler? And I guess there can be some questions around that. Another important item here is task pending time. So again, when we hand off the task to the IBM Quantum platform, for example, we do choose the system which has the lowest queue length, but by default. But we can't really tell, how long your task is going to be pending. So this is really around, doing some kind of intelligent estimating of the, looking at the queue depths and then trying to figure out what the pending time could be for some of the QPU tasks. And then the third point here is topology. You could have quantum systems from different vendors or even different models from IBM that have different topology between the qubits, and these are important metrics to consider. As well as things like the coherency and the error rates when you're doing job placement. So right now, we are kind of in the phase of collecting feedback from users. We do have, LSF has a scheduler plugin type architecture. So there's a potential for us to explore that route for for placement of tasks more effectively, potentially. So I think, there's still some areas that we're doing research in, and, we're hoping that some user feedback will help to drive that. So that's all I wanted to cover.